in the second period, nobody will come. Are you ready?
Yeah.
Okay. So, as I said, every polynomial of degree n has n roots is the statement of the fundamental theorem of algebra. But you have some additional parts. Some of the roots can be repeated. Take quadratic, for example. You can have x minus 2 all squared, right? So you have two roots, but there are two repeated roots. Understand? Some of the roots can be complex as well. That is why we say every polynomial of degree n has n roots of the form a plus bi. We're not sure. Some can be complex, some can be real roots, okay? Some can be actually purely imaginary as well, depending on if a is equal to 0 or b is equal to 0, or even both are 0. We have situation where the root is equal to 0 as well. Something like if you can factorize x out of the entire stuff, x is equal to 0 is a root. Am I making sense? Yep. So the fundamental theorem of algebra simply say every polynomial of degree n should have n exactly n roots. Okay, but because the complex number is a larger set than the real number, so we just put it in the, we assume they are in complex form. But then some may not be purely imaginary if b can be equal to 0. That's what this is talking about. So there are some properties of this stuff. So if p is a real polynomial of degree n, then the following, then p of x can be factorized into n complex linear factors. The reason for saying complex because it doesn't have to be real. But of course, you know when we say complex, real is involved as well. Complex linear factors. Okay, some of which may be repeated. Two, if p of x is a real polynomial of degree n, then p of x can be expressed as a product of real linear and real irreducible. When we say irreducible, we are saying non-factorizable quadratic. How do you know when your quadratic is not factorizable? Anyone? If your discriminant is negative. Okay, I use the notation D today, so let's use D so we can connect it with the general class. Okay, if your discriminant is negative, then it is irreducible. Actually, if your discriminant is not a perfect square, it is non-factorizable. Okay? But of course, anything less than 0 as well is not factorizable. But this time around, saying it's irreducible. There's nothing you can do about it. You can't find any factor. In fact, when you look, this is what I'm saying. When you sketch it, it is either this way or this way. It doesn't touch. So there's no way you can factorize because getting a factor means you have intercept, right? Unless the intercept are in the complex plane. Okay? The third imaginary one. So, but we're talking about real quadratic, real irreducible quadratic. So that's the so two more. If p is a real polynomial, this is just in addition to this. Maybe I should skip this. P has exactly n rows, some of which may be repeated. We've talked about that already. So if it's a real polynomial, then P plus Qi is a root where Q is equal to 0, of course. then for q is not equal to 0, p plus qi is a root. How do I say this? If and only if p minus qi is a root. So it means if one root is a complex number, the conjugate is also a root. Okay, the conjugate is also a root. That's what this is talking about. That's what happens when you have power 4, for example. If x raised to power 4 is equal to 16. The only thing you talk about is plus or minus 2, right? The other two are complex and they are conjugates as well. Okay? What this is saying is that if a complex number is a root, the conjugate of that complex number is also a root. In case anyone is confused with my notation. Okay. All right, let's write. When I say roots, of course, I'm talking about polynomial equation. Or maybe I use the word 0, since we're talking about p of x. Okay? Since we're talking about p of x as an expression. Do you understand, guys? Okay, let's use the word 0 instead. Okay, so what it says is that is, if a complex number is a 0 of p of x, then its conjugates is also a 0 of p of x. That's what this is talking about. Finally, maybe I remove this then. It's kind of affecting what I intend to write. Please remove the then. If p of x has odd degree, or should I say if n is odd? I just say if n is odd. If n is odd, then p of x has at least one real 0. Look, everyone, look at this. X squared plus 4. This polynomial is having degree which is even, right? Yeah. And this does not contain any real roots. Yeah. The two roots are complex, 2i and minus 2i. Does that make sense? So what this is saying is that if this is 3, at least one of those 3 roots, or 3 zeros, because this is an expression now, at least one of them must be a real number. It's possible the rest are complex, but at least one of them must be real. So for a polynomial whose degree is an odd number, if it is a polynomial equation, at least one of the roots must be a real number. We don't care what happens to the rest of them. It's possible it is 1, it's possible it is all. But we're saying at least 1. But this is not guaranteed if n is even. I'm just giving you an example. Okay? If x squared plus 4 is a polynomial, you can never get any real 0. Because by the time you plot it, it doesn't touch. Right? And by the time you equate it to 0 to turn it into an equation, that equation does not contain real roots. Okay? And so on like that. So that's it. So these are the main properties that we're going to be using now. I should play you this instead of. Okay, let's apply this. I just pick one question, an example. Let's see how we can apply this. You will tell me what to do. The question says 2 minus I root 3 is a root of x squared plus ax plus b is equal to 0, where a and b are constant, of course. They are divided into 3 again. Where a and b belongs to R. Find a and b. Yes, what can anybody say first? Yes, stop writing, please. Yes.
You could find the other root.
Which is?
2 plus I to root 3.
By this property, 3.
Yes.
Since 2 minus I root 3 is a root, then 2 plus I root 3 is also a root. Okay, so what do we do with this information? What does it mean to be a root?
It's 0.
A root is not a 0.
Oh, wait, no, my bad.
What does it mean to be a root?
That is x when the equation.
Say that again.
That is, the root is x when the whole equation is separated.
It's the value of x that satisfies the equation. Come on, speak like young mathematicians. The value of x that satisfies the equation. So it means when we put x is equal to this, both of them will satisfy. Is that not?
Yes.
Which means, well, this is a monic stuff, right?
Yeah.
So it could have been x minus something anyway. Is that not? So this implies that. So I can say there are other ways to do this. But this is the first thing that comes to my mind. So remember, it should be x1 minus x2, like this, because it's 0. Where x1 and x2 are these two. So we can actually say this is x minus the first one, 2 minus I root 3, then x minus 2 plus I root 3, something like that. So that is the equation. I use this format because I have 1 here. So I know it's definitely xx at the beginning. If this was 2, I wouldn't try that. Okay? Because I don't know if that 2 was divided somewhere. I don't know if that 2 is also divisible here or here. I don't know. So I can't risk it. I will have to think of another way. And another way to do will be to substitute x twice and form a simultaneous equation.
Yes.
Understand?
Yeah.
Because this is 1x, you put here, you do your complex number, whatever. You put the same x you put here, you get a and b. You put the second one as well, you get a and b. Okay? Now, there's something we haven't done. The Vieta's formula. It talks about the sum and product of roots. When we do that, you realize the sum of the roots is actually minus a, and the product of the root is b. We'll talk about that next lesson. So if you know that, you don't have to go through this approach. You just say, oh, sum of the roots, when you add these two together, you get minus a. So that means my a should be 4, minus 4. And product of the roots, and the product of two complex number is
Always real.
always real. So when you multiply this, you get b. So it will be a shorter solution, but we haven't done that sum and product of roots yet. Okay, even in the joints class, one of the things we talk about is how the discriminants can enable us find the sum and product of a quadratic equation. So without solving it, we can actually get the sum and product. Oh, I thought you guys alpha and beta on Zoom. I taught you guys alpha and beta on Zoom during the lockdown. Joey, did we do alpha and beta stuff or not? Yeah. So that's that. The sum of root and the product of roots. Yeah. So even though it's not in IGCSE, these are the areas where it is useful. That's why I said some things are not in IGCSE syllabus, but they are very, very important for foundation of IB. And we're not supposed to be wasting time teaching all that. But no worries, we'll talk about sum and product of root next lesson. So let's follow this so-called long process. Now, I'm not going to open the brackets. I'm just going to see them as one entity. So this is going to be x squared. X times this will be 2 plus I root 3 x. Then this times x will be minus 2, no, minus, there's a bracket there. Are you with me?
Yeah.
Then 2 minus I root 3 x. Then I have plus the product of the 2 now. 2 minus I root 3 bracket. 2 plus I root 3 equals to 0. Can you see that? This implies x squared. Minus is common to both and x is common to both. Right?
Yes.
So in the bracket I have what?
Oh,
Maybe I write minus x. I was going to put the x at the back. Yes?
2 plus I root 3. 2 plus 2 minus I root 3.
Oh, yeah.
Yes, yes.
Can you see that?
Yes.
Yes.
Because the minus is out.
Yeah.
So I don't need to worry about any internal bracket.
Yeah.
So what I was going to do is to put x here. But it's okay, let's put it here. I'll put it later. Then how do we do the second one?
4.
4.
4 minus 3.
Tell me how you did that.
Okay, so it's 2 times 2,
Mm-hmm.
and then 2 times I root 3.
Then you're not doing what I expect.
Oh,
Why do you have to expand? There's an identity you should have used.
oh, a squared plus b squared. A squared minus
What?
b squared.
Yeah, a squared minus b squared. So that's 2 squared minus I root 3 squared equals to 0. All these identity are like tools. You never know when you have flat tire, right? But you have the tools ready. Okay? But let's pretend we all right. So x squared minus x bracket. What is that? Is that 4?
4.
Yeah.
And then those cancel. Yep.
Okay? Then
Plus
4
4 plus
What?
minus 3. Minus.
Plus
Plus 3.
that would be minus 3, like this.
Yeah.
Let's do that first. So this is x squared minus 4x plus 7 equals to 0.
Yes.
When you now compare with x squared, it doesn't imply. Compared to x squared plus ax plus b is equal to 0, it implies that what?
A is
A
equal to
equals
negative
negative
4,
Huh?
and b is 7.
And b is equal to 7. We wouldn't have needed to do all this if we know sum and product of roots. Okay, and that's what we look at next time. So that's one sweet way to use it. Can I ask you to try number 2? I'll write it on the board. You try first, then we do it together if you can. I'll play an example for you before the end of the class. try that. Yes.
Yeah. No, it's to the power of 3. There's going to be 3 zeros. So you've got the 2 complex ones and the real one, because for putting to number 4, one has to be real. So we're going to figure that out. Right? And then we got all 3. But we can't use the method for the first one, because we don't know if the first, if A is 1.
Yeah.
So we can't do that. So we got to do some mathematical magic.
What if we do something to calculate that quadratic, and then we put this right into the next one, then we can back on it?
No, we don't know what A is, and we can't assume anything.
That's why it says find all real polynomials. So your results, you have A bracket.
Ooh.
So depending on the value of A,
I'm just going to take A out and then pretend everything inside is fine.
exactly. So it's A bracket. That's why it says A bracket.
I was saying you should zoom in. It's so, there's so much margin that's we don't need. Is that how all the recordings have been? You should always zoom in.
Because the whole point is to see the board, not to watch a movie. So you're supposed to like zoom in and make sure you cover almost the board. Maybe you watch it from 6 videos. Just kidding. But always zoom in. This is what I'm saying, guys. All real polynomials means it's going to be in the form A, x minus x1, x minus x2, x minus x3. So that's the polynomial. So we don't know what A is. So whatever A is, for different values of A, you get different polynomials. And each of them still has x1, x2, and x3 as the roots. It's like having different, let's take quadratic for example. There are infinitely many quadratic graphs that can pass through this point. Some will go this way, some will be narrower,
some will go the other way, and in each case you claim that the roots are these, but they're different quadratics. So all you have to do is you focus on the internal first, get your polynomial, then you say, oh, since we don't know, whatever, you conclude that, oh, your A is this, or better to say, the polynomial will be of the form P of x is equal to that at the beginning. Then you start by evaluating this, and at the end you get A into bracket, x cubed, blah, 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 blah. And you leave it outside the bracket, okay? Can you check the power quickly for me? Elson, could you move this?
Just for a few seconds.
Which was that one? Because I'm not sure if this one was.
No, it's the power. It has nothing to do with
Yeah, I know. So because it's powered into this one, but it doesn't seem to be working.
Uh-oh.
Have you checked here?
Is that why it's not plugged into that?
Let me
Put it back. Yeah?
Oh.
Just check here. This spring. Uh-oh.
Which one is zoom?
Some is that, yeah.
This one?
Yes, yeah. Can you see?
Ah, yeah.
Did it work?
Yeah.
Oh no, not you.
Okay.
I hope this doesn't have any on or off. Are you kidding?
The Fundamental Theorem of Algebra states that a polynomial
Now
of
listen.
degree n has exactly n zeros, real or complex, some of which may be repeated.
Is this one?
If we think in these terms, we would say that all of the quadratics we have studied in this course have two zeros. They are either real and distinct, real and repeated, or complex conjugates.
Yeah, that's fine.
More generally, we can make some conclusions for any polynomial of degree n with real coefficients. It must have exactly n zeros, which may be real or complex, and which may be repeated. We can therefore write the polynomial as the product of n linear factors, which may be real or complex, and which may be repeated. However, if there is a complex zero, then its complex conjugate must also be a zero. Otherwise, the coefficients of the